At the request of a few of our viewers, we are creating a new series here at Blue Glow Electronics called How to Read Vacuum Tube Electronic Schematics. An educational mini-series. I don't know, maybe 3-4 parts in this thing. We'll just see how it goes and see what kind of responses I get in the feedback section from you guys on how far you want to take this thing. But I'm going to have to start off kind of basic. So for some of you, this may be a little rudimentary. From others, this will be a great starting point. But hopefully, no matter where you're at, hopefully you'll learn a little something today. So stay tuned and let's have some fun. These are a few tips I'd like you to consider and maybe revisit this along the journey here in this series. But they're all tips on how to go about reading schematics successfully. First, how do you eat an elephant? One bite at a time. It's the same thing with a schematic. Some of these schematics can be really hairy, really big and daunting, very complex looking. But if you start breaking them down little piece by little piece and figure out how this piece connects to the next piece, it'll all start to make sense. You know, in general, you read them like you do a book, kind of from left to right. Typically, you see the input to an amplifier on the left, the output on the right, and the signal paths typically flowing through the circuit from left to right. It's not always the case, but that's pretty typical. Up next, schematics are not a physical layout. You cannot take a schematic, lay it down, create a circuit board from that and start soldering. They are logical diagrams, and you'll see more of that here in a minute. All points on a wire are electrically equivalent. So, if you draw a wire and it goes across the schematic, the same current flows through that wire, and voltage at one point on that wire is the same as a voltage on another point on that wire. This is a big one. While there are standards out there around symbols, lines, values in schematics, there are multiple standards out there, and often they get very loosely used, and you may see more than one standard applied in a single schematic. In other words, not everybody plays by the rules, and not everybody's even playing by the standards. So you just have to learn how to adapt as you go through these things. Pay attention to line intersections, and there's more to come on this. You'll understand what I'm talking about in a little bit. Pay attention to polarization, the positive, the negative, the orientation of something. It's important. And the most important thing I want to leave you with, the only way to get really good at this stuff is to spend time doing it. Just grab a schematic, try to figure it out. If you can't, ask questions, post on a forum about it, send me an email. We'll help you out. The more you do, the better you'll get. And I promise you, over time, you'll become an expert at this stuff. Okay, first up, I mentioned that schematics are not physical diagrams. You see right here, this is a Les Paul guitar, and it's kind of a physical layout. Here's your two pickups. It kind of shows the wires going down here. It kind of shows your volume and your tone knobs, a capacitor. But it's not a schematic. It's a physical diagram, the same as these over here are. These are physical circuit board etchings, ready to be etched onto a board with copper traces. They're not a schematic. This down here is a schematic. It is a logical diagram, and you can't just etch a board from this and print it out and install components. There's work that has to be done to kind of translate a logical diagram into a physical diagram that you're actually going to build at some point. Okay, before we learn how to read tube-based electronic schematics, you need to understand some basic electronics principles, and I'm not going to teach them in this video. You need to understand the difference between AC and DC. I've got some previous videos I've made that cover that, or there are dozens and dozens out on YouTube that you could go watch and learn about AC and DC basic electronics. You need to understand Ohm's Law. The voltage is current times resistance. Current is equal to voltage divided by resistance, and resistance equals voltage divided by current. If you don't understand Ohm's Law and how to use it, you're going to get lost in schematics. So go to YouTube and search for how to use Ohm's Law and get you a good primer on that and learn it. Okay, as it relates to electronic schematics, There's two principles out there that I recommend you go learn more about, and you can find videos on YouTube about these as well. But the first one is what I call KCL, Kirchhoffs Current Law. And what it basically says is the sum of all currents flowing into a node is equal to the sum of all currents leaving the node. In other words, the node does not either consume nor produce additional currents. What flows in must flow out, basically. And down bottom here, you've got Kirchhoffs voltage law. And what that simply states is the sum of the voltages around any given loop is equal to 0. So you can see here on this first one, you've got a 5-volt source. What that means is if you go around what's called loop 1 here, you would have to drop that 5 volts across these other two resistors. So 5 volts positive, you would drop some amount here, drop some amount here, which would take you back to 0 volts. The sum of these two drops have to equal 5 volts. The same as there's another loop here, this outer loop. So the sum of the voltages around this whole thing have to equal 0. And here's a good little example over here. If you had a 45 volt battery and you're measuring plus 45 here, and then you had a couple resistors here that are dropping the voltage across them as you go around this circuit. The first one, you've got minus 10 volts here. The second one, minus 20 volts. The third one here, minus 15. Well, if you add that up, minus 10, minus 20, that's minus 30, minus 15 is minus 45. Minus 45 plus the source here, plus 45 equals 0. In other words, the circuit itself doesn't create or consume voltage. The sum of these things are equal to 0 as you go around. Okay, up next, you need to learn various component symbols. If I were you, I would Google the word electronics symbols, then click on the images part of the little header there for Google. And you're going to start getting lots of pictures of various little templates like this, and I would start studying them, or at least know where they're at to refer to them later. But things like, this is a resistor. This is the symbol for a variable resistor. This is the symbol for a potentiometer. This is the symbol for a switch. It's the symbol for a polarized capacitor. You have one straight line, one curved line, and sometimes they'll put the plus sign here and sometimes they don't. But if they don't, it's implied that the side with the straight line is the positive side. Non-polarized capacitor, you'll just see two lines. You'll see a diode sometimes like this, and a diode doesn't always give you the positive and negative here. You just have to know that the end with this little slash on it is the cathode, otherwise known as the negative end. Battery, LED, light emitting diode. There are tons and tons of these. Start getting familiar with them, start memorizing them, start learning them. And just as you start to learn these things, and then you start trying to read schematics, you will figure out that not all symbols are created equal, but they may be representing the same thing. I'll give you an example. You see some schematics that use this little squiggly line as the resistor. You will see other schematics that use just a little square box like this to represent a resistor. A variable resistor may be one with a line through it. You may see a square with a line through it. Potentiometer, you've got a little tap on top of it here. Variable resistor potentiometer could be a box with a tap on it. You get the idea that not all these schematics symbols are used the same around the globe. This is more of a European symbol over here. This is more of a US symbol, although here they have it labeled as old resistor style and new resistor style, which is probably somewhat true as well. Okay, labeling is important, but not everyone does it well or the same. See this one right here? You've got R3, which kind of gives you each component on a schematic should be labeled or given a representative number, like resistor 1, R1, resistor 2, R2, resistor 3, R3. That way you can tie the schematic back to a bill of materials or a parts list. Then you can look up R1 is this part, R2 is this part. And boy, it would be nice if all schematics did this. They told you the value, they told you the rating in wattage, they told you the manufacturer's tolerance. You will rarely, if never, see that on a schematic. Typically, those details are left for the bill of materials or the parts list. And the schematics themselves look more like this down here, R11 1K. Well, you don't know if it's a 1 watt resistor, a 10 watt resistor. You don't know if it's 1% precision, 10%. You don't know. So sometimes you have to go to the schematic. Other times you have to, the parts list. Other time you have to try to figure it out on your own. This is pretty typical. You'll see R1 150, and you'll just know that's a resistance with 150 ohms. R2, you'll see 25 beside of it. You know it's a 25 ohm resistor. And here's another US versus European kind of thing. The US typically likes to say 4.7K, which would be a 4.7K ohm resistor. Europe seems to like this kind of nomenclature, 4K7. So you'll just know that the number in front of the K is kind of where the period would go right after that. So you could kind of look at this as 4.7, and then the K tells you that it's K ohms. It could be 4M7, or sometimes it may just say 4R. If it says 4R, that is 4 ohms of resistance. And kind of the same holds true with ground symbols. So you'll typically see this type symbol used for earth ground. In other words, that's actually tied back through the ground wire in your house back through the panel box to ground, actually. A lot of times you'll see this symbol used from where you're making an AC power connection onto a chassis for the ground wire. This typically is just known as chassis ground because sometimes the chassis is not always tied to earth ground, or sometimes known as power ground. And this is the most common symbol you will see for ground. Sometimes you'll see something here that looks like a little triangle like that, and that is signal ground. In other words, it is ground relative to something, but it's not ground relative to the chassis. And then other times, this is another one down here I see from time to time, just this little line with a flat little line on it that says, hey, this is ground. And you see a lot of variation in what people use for ground in these schematics. So here's a principle I live by. Assume all grounds in a single schematic are equal if they're drawn the same. In other words, this little symbol right here, this symbol right here, this here, this here, this here, this here, all these ground symbols are chassis ground in this case. In other words, this resistor goes from this point and then gets tied to the chassis somewhere, or it gets tied to a common ground bus. In other words, sometimes you might run a wire across through here and tag all these things together, and then you may tie that wire to the chassis. So just because you see multiple grounds in a circuit doesn't mean they're different grounds. They're all the same ground typically. Okay, again, drawing electrical connections is very important, but not everyone does it the same, or they don't even do it consistently. Let's look at this bottom schematic down here. See these lines that intersect and then there's a dot drawn? That typically means that this wire is electrically connected to this wire, same as this wire is electrically connected to these two wires. Same here, all these are connected together because these dots are showing you that these wires connect to each other. And they also use a nomenclature here in this schematic where if you run two wires across each other and you don't put a dot, instead you put this little jump, like, hey, I'm jumping over this wire. That's one way to indicate that these wires are not touching these wires. They just, for simplicity of drawing the schematic, they have to be able to cross each other, but they are not electrically connected. Then you come up here and look at this top one. That's connected, that's connected, that's connected. But then down here, they show this wire coming over here to this transistor, this wire coming over here to this transistor. And the fact that they did not put a dot, even though they didn't put a jumper, means that these are not electrically connected. Those wires have nothing to do with each other. So most of the time when you see two wires cross each other and there's not a dot, it means that they are not connected to each other. However, look at this. They even broke their own rules here. They showed three wires being connected together, but they didn't put a dot. Frustrating, but that's the way a lot of people do schematics. They're not consistent. They're not always standardized like they should be. So you just kind of have to get used to it. Here's a few more examples to kind of further confuse you. On this one, these wires are connected, but they're not showing a dot. And anywhere that there's not a connection, if you'll notice, they just show a little break in the wire right here. the same as they show a little break in the wire there. Doesn't mean that the wire is broken. It's basically the same as I showed you before. They're basically jumping either on top of or behind that other wire. So in this case, you know, this connection goes all the way from this 10K ohm resistor into pin 5 here of this chip, but there's no breaks in the wire, and they're not connected to that wire or that wire. And over here's another good example where they are using the dots and they are using the little jumpers here. So I kind of like this schematic. I think they did this one right here. And one last thing about wire connections, typically done with voltage connections. They're not always drawn, often they are represented. Let me give you an example. This, by the way, just happens to be the single-ended amplifier that I'm doing a series on right now as well. But this is the power supply down here, and it produces a couple different voltages. First off, it produces B plus at 450 volts. It also creates something they're calling B plus plus at 350 volts, and it also creates B plus 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 or B plus plus plus, yes, at 300 volts. So 3 different voltages here, 450, 350, 300. But then when it comes up here to the actual amplifier schematic, they don't actually draw wires from here coming up around. What they do is they say, hey, B plus 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 connects here, B plus plus connects here, and B plus connects right here. The same as they also told you here, you know, coming out of this little secondary of the transformer, they're feeding over to something called global feedback, and they showed an asterisk. Well, then over here, they showed global feedback. It's coming back in right here. So they kind of broke the long wire that would have to come along here, and they're just kind of saying, hey, it left off here, and it picked up right here. All right, this is the closest I'm going to get to teaching something outside of this, the core of this, but you need to go watch some videos on how tubes work. There's a couple old military ones out there, even though they're from 1940 something, they're really good videos. Just do some searching on how tubes work. But typically in a tube, this is a symbol up here for a triode. You have a cathode, and then you have a grid, and then you have the plate, otherwise known as the anode. And what happens is typically current flows from the plate to the cathode, and that gets controlled by, sometimes you hear tubes called valves. Well, they're called valves for a reason. It's because this little thing here is called a grid actually has the ability to shut off the current flow coming from the plate to the cathode here. And a good example of that is if you grab the knob on a spigot of the water spigot at your house and you turned it wide open, you might get a spray of water out of your hose pipe 10 feet long. And then you may turn this handle, I'll just give you an example, like a 1/4 of an inch back or a 1/2 an inch back, and all of a sudden you've only got water flowing out 1 inch here. And then you turn that knob, you know, back a 1/4 of a turn around, maybe you turn it a 1/2 an inch, and all of a sudden you've got 10 feet of water. So just a little bitty movement, maybe a 1/2 or a 1/4 inch or something here in this little knob, actually changes the flow of water from like an inch to 10 inches or 10 feet. The same is happening in a tube here. Your input voltage here is either positively or negatively biasing this grid, which turns on or off the flow of current through the tube. And if you've got a tube, let's just say it's got 250 volts sitting right here on the plate, and you're turning that 250 volts on and off by this little bitty voltage. Typically this input voltage over here would be maybe a 1/2 a volt. But yeah, that 1/2 a volt swing is able to control a huge swing on the output at the speaker over here of maybe 250 volts. It's significant. One little thing moving controls something much, much bigger, and that's what tubes do, and that's known as amplification. One thing you note here, this little thing here called a filament, the way tubes work, they have to get heated up on the inside. They're inside of a vacuum sealed glass enclosure, typically with all the air and impurities removed. And then once you heat this filament up, it gets the tube hot on the inside. That's what lets the current flow through the tube here. And if you'll notice in this schematic symbol, we see 6.3 volts sitting here to heat up that filament to get it hot and perform that function. something you should probably read about or maybe find a video at some point is about the difference between electron flow and conventional current flow. Typically in a tube, the electrons actually flow from the cathode to the plate, but our typical nomenclature of how we show current flow is from positive to negative, and so typically we say current flows from the anode through the tube to the cathode. And a couple different tube symbols you'd see here. A diode. In other words, there's just two conductors on this thing. You've got the plate and the cathode, and there's really nothing connected here in between. And then you got the filament here to heat up the cathode or the tube. And then you've got a triode. So diode, and di stands for two, bi. Triode, three connections. So here you would have the cathode, you would have the plate, and you would actually have a grid that kind of help control the flow through that. Then there's something called a tetrode. You get into 4 elements. This has an extra little screen here that's used for various purposes. And then you can get into a pentode where you've got 5 connections here, and then this one has another screen here used for various purposes. I'm just trying to teach you all these anomalies you see out there because they are what trip people up the most. Let me give you an example here. Filaments are not always shown on tube amp schematics, nor are the pin numbers on tubes. For example, this is a triode that you would see. It doesn't show the filament connected to it. It doesn't show what's pin 1, 2, 3, 4, 5 on this thing. You just kind of have to know from the symbol here, this is the plate, this is the grid, this is the cathode. Similarly, this one shows plate, grid, cathode, but hey, it shows the filament, but it doesn't connect the filament to anything. Sometimes this is used to show that this is an indirectly heated triode, and we'll talk more about that in a minute. A couple things to notice here. One, this schematic here, this little symbol shows 2 tubes inside of 1 tube. There are a lot of tubes out there that are like, this is called a dual triode. It's got 2 tubes inside of 1. And I also wanted to show you here that in a dual triode or a dual part tube, a lot of times they will have multiple ways you can connect up the heater voltages. In other words, you could connect the 12 volts across pins 4 and 5, and it would heat up both cathodes here and light this tube. You could also connect in the very middle to pin 9 and tie pins 4 and 5 together, and then you could feed this tube with 6.3 volts. So a great example would be the famous 12AX7. You can feed that tube with 12 volts, or you can feed that tube with 6 volts, just by the way you wire up here the filaments. And a neat little configuration here, if you've got a dual throw switch here, you can actually wire up a switch so that you could do tube rolling. Maybe you had an amplifier that could use like 12AX7, or you could flip the switch and then put in a 61NP in its place, because then it would be being fed by 6 volts. And a good example, most tubes can either be fed via AC or DC. So you could feed these filaments with AC or with DC. They don't matter. They light up the same, and they get hot, and they heat the tube up, heat the cathodes up here, and cause conduction to start flowing. Okay, some tubes have the cathode directly heated, but most modern tubes have indirectly heated cathodes. And what I mean by that is you actually have a wire inside the tube that is the cathode, and separate from that is this heater connection, the filaments. The filaments get hot, and they're very, very close physically, and they heat up the cathode, and then the tube starts conducting. In some older tubes, and I listed some above here, the famous 2A3 or the 6B4G, let's see, the type 50, type 45, 811s, the 211s, 845s. A lot of these tubes, they are known as directly heated cathodes. In other words, not only is the cathode here maybe have voltage, current flowing through it from the plate, but you're also feeding it with, let's say, a DC voltage or an AC voltage here to actually heat it up. And So you don't run into that as much in modern tubes, but if you're working with any of these old famous, you'll hear these typically called single-ended tubes, single-ended amplifiers. You'll run into these directly heated cathodes quite a bit. And sometimes you'll see a symbol here that'll just show the cathode looks like this. Typically that means it is an indirectly, even though they don't show the heaters separately. Okay, I'm just showing you here. So a great example, all of these symbols on the top up here are tetrodes. This shows your cathode, your two filaments, your grid, a screen, the plate. Same thing here. This one's actually a beam power tetrode, and you can tell that by these two little angled things right here. That typically means that they're tied back to the cathode, and they're actually forcing a beam of electrons through to the plate. And so you'll see a slightly different drawing. And the same down here. This is a pentode, a drawing of a pentode. This is a drawing of a pentode. So you just have to get used to variations in tube, what they look like on schematics. But once you kind of get used to it, you'll realize what all is the same and what's not. Okay, see this little picture right here? If you're ever curious, you find a schematic and you don't know what the pins numbers mean, or sometimes they don't even show pin numbers, go look up an example here. Type in 12AX7 space data sheet, all one word, data sheet. Hit enter, it'll bring you up some links to data sheets. You'll find a little picture like this that'll tell you what the pins are, what the connections are for that tube. But sometimes in the schematics they're not so clear. So here you see this is a dual triode. Here you see pins 1, 2, and 3, and then you see 6, 7, and 8 over here. And these things are kind of separated from each other in the schematic. Here's another example of the exact same thing. You see a fully drawn circle over here that looks like just a single triode. But then you realize, they didn't really label this tube. They didn't really label this tube. This one uses pins 1, 2, and 3. This one uses 6, 7, and 8. Then you notice in between them here, they wrote 12AX7. What you come to realize is, even though this looks like two separate tubes, this is really two tubes inside of one glass bottle. The same here. This is a great representation. They kind of show a dark line to show this is half the tube, and then a gray line to show, hey, it's only part of a tube. And up here it tells you it's half of a 7025, otherwise known as a 12AX7, and then over here. So I really like the way they've done it here on this schematic. But you'll find all of these as you're scrolling through various schematics. Okay, all the excitement's been building up to this. We're going to get into a circuit example here today. And most of my videos beyond this one will be us just walking through various circuit schematics. I want to do a single-ended amplifier. I want to do a push-pull, maybe a parallel push-pull, maybe some preamp schematics, maybe a guitar tube amplifier schematic, and kind of go from there. But this is one... Michael Abdullah, it's a famous little KT88 single-ended amplifier. If you wanted a great starting point, this would be a great amplifier to build. But a couple things about what you see here on this schematic. First and foremost, this is only one channel of this amplifier, even though the schematic only shows one channel. But if you actually wanted to build this as a stereo amplifier, you would have to duplicate all of this in the chassis, one for the left channel, one for the right channel. But the schematic doesn't show that or tell you that. It's just something you have to kind of intuitively know, that sometimes they only show you one channel and you know you would have to duplicate that. Likewise, this one doesn't show the power supply for this thing. It just kind of tells you that there's a B plus right here that feeds into this this output transformer, and the B plus needs to be 400 volts. Now later on in his work, he does show you a sample schematic for the power supply, but you could build a different power supply if you wanted, as long as it provided 400 volts to this point right here and this point right here. So before we walk through this schematic, let's take a look at a couple things. First off, there's two tubes here. You kind of recognize both of these as tube schematics. By the way, this is one of those beam power tubes we talked about earlier, because you can tell by the little angled things right here. And this one says it's half of a tube, half of a 6N1P right here. So oddly enough, if you were actually building this thing, you could use one glass tube and use half of the tube for the left channel, and maybe down on the other side of the amplifier, the other half of that tube for the right channel. And then you would need two tubes here on the output, a whole KT88 for the left channel, a whole KT88 for the right channel. So at the end of the day, this could turn into a 3-tube amplifier. I hope that makes sense to you. If not, ask some questions. So before we look at what everything here is, let's look at what's missing. You notice anything odd here? Well, on the tube, it doesn't tell you pin numbers. So you don't know if this is pin 1, pin 3, pin 5. You have no idea. So the first thing I did when I pulled this schematic out was I went and pulled up the data sheet for both of these tubes. And what do you see? Here is that 6N1P. It kind of tells you that, pin 1 here goes around to the plate. And sometimes these things are hard to follow. Pin 2 here goes to the grid. Pin 3 here goes to the cathode. And you can kind of see that. It'll tell you anode or plate, grid, cathode here. And then pins 4 and 5 here are the heaters. But remember we talked about earlier, because they feed around to right here and right here. You could use pin 9, tie 4 and 5 together, and then go from those two tied together to 9 and feed this tube with 6 volts. And then you got the other half of the tube over here. Similarly here on this KT88, you've got pins 2 and 7 that go to the heaters here. You've got pin 8 that goes to the cathode. You got 5 here, which is grid 1, 4, which is kind of the screen here. Then you've got pin 3, which is the plate. And then the second screen here, which are beam-forming plates, they're tied back down here to the to pin number 8 internally inside the tube, so you can't really do anything about that. But kind of gives you a feel for then what the tube, the layout is, if you needed to know the pin numbers. Okay, let's do a little walk left to right and just identify the components here. This little symbol is typically shown as an input signal for an RCA jack. The little center connection here is the middle part of the RCA jack, and this outer part here is typically the shield or the outer part of the RCA jack. And typically, not all the time, but typically they are tied to ground. You feed in from that then into this thing right here, which happens to be, if you look up the schematic symbol for that, it is a potentiometer. And this potentiometer is kind of tied between this input and ground, but the tap of the potentiometer then feeds over here to the grid of this first tube. And what this forms right here is a little bit of a voltage divider between wherever this resistor is connected here and wherever the wiper's at on that potentiometer versus the other connection of the potentiometer and where that wiper is at. In other words, if you turn the wiper all the way up to this side of this potentiometer, then 100% of the voltage feeding in here would feed to the grid of this thing. And if you turn the wiper all the way down here to the other side, then theoretically 100% of this potentiometer would feed straight to ground. In other words, this is a volume knob. If you turn it all the way one way, it's basically sending your signal straight to ground. None of it's going through the amplifier. You have no signal, thus feeding the amplifier. Thus it is quiet. The other one, you've turned it all the way. You're sending none of your signal to ground. You're sending it all straight through the amplifier. You have full volume. This is how you make up a volume control. Okay, so up next, something you'll learn about when it relates to tubes is there's something called tube biasing. And basically biasing is getting this tube at the right operating points. In other words, the right voltage on the plate, the right amount of voltage here on the grid, and the right amount of voltage sitting here on the cathode here of this tube. If you do some Googling YouTubing on how tubes work, you'll typically learn about biasing here. And maybe if you guys wanted me to, I'd do a video just on biasing tubes. But it's the purpose of this tube. It's to drop some voltage across right here prior to the plate, and it's also to serve as a load resistor for the plate. And one thing that's interesting here, I'm going to point out to you, notice this says 2 watt, 47K resistor 2 watt. We'll come back to that in a minute. But basically that load resistor here is connected to the plate of this tube. Then you got one coming from the cathode down to ground. This is typically called your cathode bias resistor. This, when you see a tube biased this way, where you're using a tube here to set the conditions, and the typically biasing is defined as the difference in potential of your grid to your cathode. And what this thing actually does is takes a voltage drop across this cathode resistor here, which creates a different potential between it and the grid and biases the tube properly. And so you typically pick a value to do that, and how you go about picking that value is outside the scope of this realm. But notice here on this resistor, it just says 1K, and it does not tell you what size resistor that is. Well, by default, if I don't see a value, I personally, when I'm dealing with tube gear, I kind of assume a 1/2 watt resistor. You might get by with a 1/4 watt, but I like to assume a 1/2 watt resistor. Other people assume a 1 watt resistor. It just kind of depends, but I'll show you here in a minute how we could actually figure that out. And then what you have flowing in parallel with this resistor right here is what is known as the cathode bypass capacitor. And in this case, it tells you it's 100 microfarad at 25 volts. Don't worry if I'm losing you, stick with us. As we go through more and more of these, you'll start to pick it up. But remember earlier I mentioned I was trying to figure out the value of this resistor, what wattage rating it needed to be, because they specifically called this one out and they didn't this one. Well, if I wanted to, I could use Ohm's Law to figure that out. I know there's 400 volts sitting right here, and I know that the voltage goes through this, or the current goes through this tube to ground. So it pretty much has to flow through this resistor and this resistor. And this is a 47K and this is a 1K, and resistors in series add, so that's 48K. 400 volts divided by 48K brings you out to be about 8.3 milliamps. And then if you used Ohm's Law, remember what I told you earlier, current flowing through here would have to equal current flowing through here for the most part in a tube. It's a good assumption that your plate current is equal to your cathode current. You do get a little bit of current coming in here from your grid to add to it, but for the most part they're equivalent relatively. So you could say whatever current's flowing through that is flowing through this. So that 8.3 milliamps flowing through this tube. Well, then if you did the math on that, what you would end up with is that 0.0083 milliamps squared times 1,000, and you come up with a total of 68 milliwatts that would be consumed by this resistor. So a 1/2 watt is 500 milliwatts. 68 milliwatt is not going to overheat something that can handle 500 milliwatts. So my 1/2 watt assumption here was a good one. Okay, and up next you're going to flow out of the plate of this tube with the signal. The audio signal actually flowed through right here, went through this potentiometer, went through the grid, got amplified as part of this tube. In other words, the little bitty things moving right here, the little AC voltage, is causing a great big AC voltage over here on the plate. And then that amplified signal is moving along. And what you don't want, if you notice, you had B plus 400 volts sitting up here on top of this plate right here. You don't want 400 volts sitting right here on the grid of your next tube. So you use something here called a coupling capacitor to separate this stage of the tube from this stage of the tube. If you remember, from your capacitor education. Capacitors block DC, but they allow AC to flow through them. So your audio signal, the amplified one, is flowing right on through here into the grid of this next tube. But all your DC, the 400 volts sitting right here, is getting blocked. That's why when coupling capacitors are old and they start to break down, and it lets 400 volts leak through when they become leaky, and then it sits on the grid of the next tube, all of a sudden you've got a KT88 that's glowing orange on the inside. Sometimes they call that red plating. And your tube is basically sitting there burning up because you're putting 400 volts where there should not be 400 volts. This grid is typically, a slightly negative voltage compared to the cathode here. Okay, and up next then, you kind of feed, like I told you, into the grid here of the next tube with your audio signal. Keep in mind, really little signal, maybe 400 millivolts feeds into this tube. Maybe it comes out the other side of this tube at a volt or 3 volts, feeding into this KT88. And then you got this resistor here. This is called a grid leak resistor, and kind of the purpose of this resistor is to help in the biasing of this tube, as well as this grid gets kind of bombarded with electrons, and it needs a place for those electrons to kind of leak back off to ground. Then you end up with your, similarly as the last one, your cathode resistor here that's biasing this thing, your cathode bypass resistor here. You can actually run an amplifier without the cathode bypass, but it greatly impacts kind of your overall sound reproduction of this tube. And then if you'll notice, you're feeding out the plate of this KT88 with a much amplified signal. It may be hundreds of volts right here at this point. And it's feeding over into the output transformer, which is tied to the B+. And that's how it gets fed to the plate here. So in other words, instead of having a load resistor, this transformer becomes your load resistor. And it tells you here that your Z, in other words, the impedance of the primary, which is this side over here, is 5K. So instead of having a 47K ohm load resistor on this tube, you have a 5K ohm inductor basically as your load. The secondary of this transformer here has an 8 ohm secondary, and what this is doing, it's an impedance match between this tube. The output impedance of this tube is probably up around 5,000 or 6,000 ohms, and you're trying to match that up with a device that operates at 8 ohms. So not only is it doing impedance matching, it's also doing voltage conversion, because you may be feeding hundreds of volts right here out this output, and it would convert it down to a voltage here that if you actually touched it at your speakers would not fry you to death. In other words, it could be 20, 30 volts here going to the speaker. One last little odd thing you see here, and you'll see this done from time to time when you're dealing with pentodes or tetrodes, is you'll see what's called an ultralinear tap coming off of this transformer that basically takes a little bit of the output being fed and feeds it back to one of the screens in this tube, and it's a form of negative feedback in this amplifier here to kind of stabilize it, equalize it, and broaden the bandwidth of this amplifier. And just a few things to note. This B+ point right here that's sitting on top of this transformer feeding the plate is electrically equivalent to this point right here, this B+. So both of them are getting 400 volts. This one's getting dropped down a little bit by this load resistor here, the same as you're taking a little bit of a voltage drop across this load resistor here as you're feeding in. You've got ground, 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 ground. All these ground points are tied equally together, the chassis ground on this thing. And that's kind of it. That's kind of the whole schematic, one side to the other. Keep in mind, if you want to build a stereo amplifier, you'd need 2 of these whole phases. And you'd also have to build a power supply. We'll walk you through a power supply in one of our upcoming videos. And sometimes you hear people talk about the signal path or components that the signal actually goes through. So you've got I drew a red line here. You've got the audio feeding in here, kind of goes through the grid of this one, comes out the plate of this tube, feeds through, goes through this coupling capacitor, goes through here, kind of comes out this tube, goes through the output transformer, gets induced into the secondary and feeds the speaker. So if you're thinking about components, if you were building this thing, that the audio signal actually passes through, and so you want to buy really high quality components, it goes through this potentiometer, it goes through this tube here, goes through this coupling cap, goes through this tube, and it goes through the output transformer. None of these other components here does the signal path go through. Doesn't mean you don't need good quality components there. I was just showing you the ones that the signal path actually flow through. Hopefully you've learned a little something today about reading tube amplifier schematics. We'll keep going with this series and go into some more examples in the next videos. Please post comments. Tell me what you're missing. Tell me what you'd like to see. Tell me what you don't understand. Tell me what I'm telling you too much of or too little of. Thanks for watching, everybody. I hope this is a fun little series. I know I'm having fun with it myself, and hopefully people are learning something. So stay tuned, and thanks again for watching.